So this next one is variations. So we have a drop factor, we have an order for infusions, and somewhere down the road something went wrong, changed it, and you have to readjust. So that is this video is about. I wanted to show a little bit of physical stuff so that you can understand it better. So we have our IV bag. This one here is 1,000 milliliters. Of course, it has around 400. 1, 2, 3, 4, 5, 6, 600 milliliters in here of water. So this is our IV bag. This usually changes. I mean, they come and refill the IV bag during the process if you need more. This here, though, this is what's connected into it. All this here is called the drop factor. And it connects into the patient's IV. We have PICC lines where if they have to come in and give you medication, painkillers, or antibiotics, or whatever it may be, they put it in through the PICC line. This right here is where it shows the actual drops from here. I got it closed off so it don't go everywhere. But once you get it set, you'll see the drops drop through here. Now they have a drop factor of 10, 15, 20, and 60. So the smaller the drop factor that we're working with, the bigger the drops are. The larger the drop factor gets, the smaller the drops are, which makes sense because we're talking about drops per milliliter. This one here, though, I actually take the bag on here as 10 drops per milliliter. This here is my drop chamber. So if you're using gravity instead of a pump, you'll have to set it yourself. You'll need a second hand. You'll have to calculate how many drops per minute you're going to give, and make it easier then when you go to the minute, figure out how many drops that will be per second, and then watch your second hand and roll this up and then count the drops and get it within that time. And this is your drop chamber. So during the process, just a little quick reminder, they can change out the IV bag, but the drop factor doesn't get changed out. It's connected to the IV and to the patient. And unless something really bad goes wrong or they have to replace it. But usually that doesn't get replaced. So let's solve for this one. It says we have an order of 500 milliliters IV with an infusion or flow rate of 45 milliliters per hour. And we have a drop factor of 20 drops per milliliter. And the drop factor, again, is what I was showing you. The only thing we don't know here is how long are we going to infuse for. So we need to solve for the infusion time. So what I'm going to do is I'm going to take the volume of the IV bag that they said. And I know they make IV bags different sizes. So a 500 milliliter IV bag, they really wouldn't have to have 1,000 milliliter. They can get a 500 one. But if they used 1,000, it's usually they mark it off so that way they can make sure and only administer. Plus, you also figure out how much time you need to do it for. You need to figure out the flow rate. So there's many things that play factors here. So let's solve for the infusion time. How long you're going to infuse for. You got the 500 milliliter from the order times my flow rate, and we're solving for time. So I'm going to put the H on top and the 45 milliliters on bottom. And I'm able to mark out my milliliters. I did great. Now we have 500 times 1 divided by 1 times 45. That gives me, and I'm going to round to the nearest tenths. And I only ask my students to do that on the time in our class so we can all be on the same page. But wherever you may go, you can adjust because you can do the math. So it's 11.1 hours. I like for you to elaborate, make a statement on it. It's 11 hour, and then tell me how many minutes. We're going to keep this one. I'm going to make a note over here. 11.1 hour, and that's going to be my original time. My original infusion time. So that's my side note. So as we go, I don't have to, because I'm going to have to erase the board as we go. But how many minutes is that? Well, we're going to take the 0.1 hour and let's convert it to minutes. We know for every 1 hour, it's 60 minutes. If we're solving for minutes, it needs to go on top, hour on bottom. And if I'm able to reduce this, we did great. 0.1 times 60 is 6 minutes. So on your assignment, you would make a statement. You would say 11 hour, 6 minutes. If you put a 0 in front of that 6, just be very careful about it, okay? About your notation, and make sure you have an appropriate space. So 11.1 hours is how long it's going to take to infuse. I'm going to erase now. So I want to know how many drops per minute. So this can be in my original flow rate in drops per minute. So what I'm going to do is take my 45 milliliters over 1 hour. I'm going to times it by my drop factor. I have 20 drops per milliliter. And again, I asked for drops per minute. At the beginning when I asked for drops per minute. We've got two options. You can erase that 1 hour, because we know in 1 hour is 60 minutes, and you could put 60 minutes right there if you wanted. Or we can set up our conversion. In 1 hour is 60 minutes. Go through there, marking out the units that we don't need, and we got drops per minute. We set it up correctly. Now I have 45 times 20 times 1, all divided by 1 times 1 times 60. And that gives us 15 drops per minute. So this is my original. I'm going to draw a line. I'm going to put original 15 drops per minute. We'll need this later on since we're doing variation. So the next part says after, let's see, how much time do I want to say? After, let's say 2 hours. After 2 hours, we have a remaining volume of 395 milliliters. So something went wrong, guys. Yeah, my sloppy writing there. We got to be a little bit neater. Something went wrong throughout this process. We don't know. Multiple things could have happened. But we know that 2 hours into the infusion, something happened and we got this remaining. So we still got to finish infusing all of that order, which is 395 left. So we need to refigure out the infusion time because that changed now. So we said that 11.1 hours, which is 11 hours and 6 minutes, right? And it said 2 hours later, so I'm going to put the 2 hours underneath that. There's 0 minutes, right? Didn't say anything about minutes, just said hours. So I'm going to bring down the 6 minutes. And I got 11 minus 2, which is 9 hours. So this is what we would say 9.1 hours. I'm going to come over here and I'm going to say adjusted ADJ, or you can say recalculated 9. Let's write this neat enough we can read it. 9.1 hours. And I'm going to erase this so I can have room to do the next part, because we got to adjust, make an adjusted flow rate and adjusted flow rate drops per minute as well, and then we got to determine the variation if it's safe or not. Alright, so now let's figure out the flow rate milliliters per hour. If we have a remaining volume of 395 milliliters, and then we have this 9.1 hours left, we're going to say 395 divided by 9.1, and that will give us, and we're going to round to the nearest whole number. Guys, the reason why we round on this infusion is because we can't take half of a drop. Or a 3/4 of a drop. We're not going to be able to just cut it off in mid-drop. So we got to round to the nearest whole number. So I'm going to round this one to the nearest whole number, which gives me 43 milliliters per hour. So here is my original. Oh, excuse me. My apologies. This is my adjusted, my recalculated flow rate. So I'm going to call it adjusted. 43 milliliters per hour. Now let's find the adjusted recalculated drops per minute. We're going to take that 43 milliliters per hour. And again, for those of you that like shortcuts, you know that's 1 hour. We can replace that 1 hour with 60 minutes. Or we can add on a needed conversion. The part that I said did not change was the drop factor. Remember I showed you at the beginning. That is 20 drops per milliliter. And let's add on our needed conversion. We know for every 1 hour it's 60 minutes. I'm going to go through here and make sure I can mark out what I need to. I'm left with drops per minute. I did it right. Now I got 43 times 20 times 1. It's all divided by 1 times 60. And we're going to round to the nearest whole number, which gives us 14 drops per minute. And this is going to be my adjusted. So I can erase this. So now here we're going to do the last part. The last part is the variation, and I'm going to give you the formula. And why is the variation important? It is important because we want to make sure that our adjusted flow rate and our adjusted flow rate of drops per minute and milliliters per hour is safe for that patient. We don't want it to be too fast. We don't want it to be too slow. We want it to be just right. And so in order for the doctor to go ahead and give that order, and the nurse and whoever administers, they've already looked at it to make sure that the order was safe. So it's already been looked down by multiple people to make sure it's safe. Well, when you have to make this adjustment now, you need to figure out if the adjusted's going to be safe. So you're going to do the same process, except for as far as checking. But we have a formula for this one. All right. So to figure out the variation, it's going to be your adjusted, or you can call it your recalculated, minus your original, all divided by the original. And we're going to multiply it all by 100%. So if you need to write this down, pause it, because I'm going to erase it so I can use it. But it's the adjusted minus original divided by original. And what part of the adjusted original are we using? The drops per minute. So I'm just going to erase these words right here. Put in place what I need. So my adjusted is 14 drops per minute. My original is 15 drops per minute. And it's all divided by the original drops per minute. So whenever we add or subtract, we have to have like terms, or you can't add them or subtract them. So I'm going to put my hand over the 14. I got drops per minute. My hand over the 15 drops per minute. So they are like terms, so I can subtract those two. So I'm going to rewrite it as 14 minus 15 in the parentheses. And I'm going to put my drops per minute like this. I'm going to rewrite the whole thing because I'm going to show you where the basic math comes into play. Which basic math comes in play all the way, but I'm going to show you what happens to those units. And I got divides. Yeah, we're going to leave that. 15 drops per minute. All right, of course, we can clean that up. 14 minus 15 is a negative 1. And then we have drops per minute. And whenever we divide by fractions, there's a rule. We're going to keep the first term the same. We're going to change this operation from division to multiplication. And we're going to flip this second term. So change, flip. And what happens? Well, we can reduce. The drops reduce, the minutes reduce. And it leaves me with negative 1 times 1 over 1 times 15. And then I'm going to bring this 100% down here and say times 100%. And just to be consistent in this class, I'm going to round to the nearest whole number. So it's a negative 7% variation. And let's talk about what that means. And there's an action plan. So some places will say they have a protocol of the variation cannot exceed 25%. And if it's between 0 and 25%, they call it good, safe, we're okay. If it falls below 0%, then that means that it's a negative number, and that's what we have here. Then that means the adjusted rate is set too fast, and we need to decrease it. If this number, this variation number, was over 25% based upon this protocol, then it would be, the adjusted rate would be too slow and we need to increase it. So my action plan, and you would have to make a statement, is that my variation is a negative 7%, and that negative tells me that the adjusted is too fast. We need to decrease the flow rate, and then we'll have to go about the protocol on that. And that is solving for variation.